Hello everyone. So the idea today is talking about the 7702, this new EIP that's coming in the upcoming hard fork for Ethereum. I was told to say that it's pretty simple, but it's not. So today the idea is to make a walkthrough of it. Not only staying on the theory of 7702, but actually going deep into the code as we usually do at the Red Guild, trying to understand not only the benefits of the EIP, but actually risks and security threats and things that developers might get wrong when they are implementing account codes. So hopefully after this video you will get a sense of the footguns, the risks, the threats, and hopefully some ideas to implement more secure account code. We will also be giving some examples of work in progress, but what seems to be more production ready code for account codes for 7702. Credits where it's due. So there's a nice talk at DevCon by Light that goes into 7702. I wouldn't say it's too technical, so don't be afraid by the title. I think anybody could watch it and you will easily understand what 7702 is about. If you haven't, I'm not gonna read the whole EIP today. So probably you should stop the video, read the EIP, and then come back. But yeah, if you don't like reading and you like watching, probably this talk is a good start for you. Okay? Then I will also be using some resources by the Ithaca team, which I think has been putting out cool stuff related to 7702, particularly this repository about Odyssey examples. Odyssey is a DevNet, also a public testnet in which you can try out different EIPs such as 7702, and we will be using that today actually. And they have been putting together also some write-ups and articles on their blog, which are quite cool, and they are useful as triggers, as ways to kickstart your journey into 7702 and understand different possibilities, implementations, and features that we can actually have now in, well, not now, but hopefully in the near future in Ethereum. So to begin with, we can actually do this. Okay, this is the agenda for today. What we have today, what we could have with 7702, then going over 7702 with some diagrams and the things that you're used to from us. Then we will be using Cast, Forge to see what features we already have in this development tooling, so as to be able to use 7702. And then we will be going over a lot of bad code that we have put together, so that you get an idea of what can go wrong. At the end, we will do some walkthroughs, one of Geth, for example, and also some walkthroughs of hopefully more production ready code that people are starting to build right now. If we want to talk about the current state of stuff, we should probably make this big distinction between smart contracts and EOAs. You probably heard about it, so I'm not gonna go into depth, but suffice to say that externally owned accounts are those that today have a private key, and smart contracts don't have a private key. Externally owned accounts don't have code on the accounts. Smart contracts do have code on the accounts. Let's say that's about it. All right. So if we want to actually look at that in a more practical way, what we can do is actually, I have this contract right now, and what I will do is I can deploy this, and we're missing the from address. From, let's use this one. Right? Perfect. So I'm creating a contract. I'm actually deploying this contract into my Anvil instance. I've just deployed it. So actually, if I want to check the code on the account that deployed on the contract, we will of course see that there is no code. But if we want to check the code on the account where the smart contract lives, we'll see that there is code. So big distinction that we have today. With 7702, we want to change this. With 7702, what we want to do is that not only smart contracts will be able to have code, but actually external accounts will also have code. So probably we should stop making this big distinction between smart contracts and external accounts, because this limit between these two is about to get more blurry, if I can say that. That's a very easy way to understand this difference between these two. EOAs are quite limited, but they are simple to use. You have a private key, you can execute transactions from it, you can talk to smart contracts, you can trigger transactions to do stuff on chain, and smart contracts have the code that will define the mechanics of what will happen during that transaction. That's not enough. So perhaps what you want to do is you want to batch operations. Perhaps you've sometimes been in a place in which you want to send ether or tokens to many of your friends, and you cannot do that in a single transaction easily. Or you want to do swaps and deposits and withdrawals and like multiple DeFi operations in a single transaction, and that's also not easy to do from your externally owned account. Perhaps you've found yourself in a place in which you don't have gas to execute a transaction, and it's difficult sometimes to get gas, and that makes the whole onboarding more difficult. So it would be nice to have a way to sponsor each other's transactions, such as I could pay for your transactions, or you could pay for your transaction in tokens, for example. Also, it would be nice to execute transactions or be able to sign transactions with different mechanisms. Today we are implementing one of the ESA curves, but perhaps we want to implement some other way of signing transactions. And we could do that too with 702. There's also this idea of having accounts with different roles, such that the fact that somebody has power over your account doesn't necessarily mean that that power will be infinite and will be able to do everything with your account or forever. So there might be a way to reduce the privileges that somebody using your account can have. That also can happen with 702. You could implement like more native multi-sig stuff into your account. You could have guardians. You could have less privileged roles. I don't know, you are allowing a friend to execute one transaction a month from your account. That you can do with 702. And then we could go on talking about this idea of sessions, this idea of subscriptions. You can actually subscribe to some service with your account, and that service will actually take money monthly from your account. So the EIP is this one. Again, you should probably read it. You should probably understand what's going on with this. It's not that complex, but I think the consequences of the EIP are far more complex or interesting than the EIP itself. One thing to take into account is that we are introducing a new transaction type. And in this new transaction type, we will have new fields, right? We will have what we call the authorization list. In this authorization list, you will be able to make a signature such that you will be authorizing to deploy code into your address on a certain chain. You are not. It's worth noting that you are not specifying the code that you are deploying into the account, but you are actually specifying the address in which that code lives. So that means that that's kind of a pointer. Right? So that means that I could be using the same code as you are using for our accounts. And that's probably what's going to happen. We will all be using similar code for our accounts. We can also talk about later about the consequences of that and how wallets can play a role into that. But again, suffice to say, the fields are pretty similar to the other transactions. You have the chain ID, the nonce, the max fee value, data, blah, 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 blah. But we have now the authorization list, the chain ID, the address, a nonce, and a signature. Alright? The EIP goes on explaining exactly how the kind of in pseudocode how the whole authorization mechanism will go, and that how the opcodes should behave after once you have set code into your account, and then over the gas costs and so on and so forth. The theory is nice, but it's actually nicer if we can actually take a look at a real example into this. So for this example, I based myself on this repository. I'm gonna go over something very similar to this. So kudos to Ithaca team again for putting together this repository, which is very easy to understand and very easy to actually set up something quick for you to try it out what I'm meaning with all of this. I have some diagrams later that I can show you, but first I want to show you the thing in action, and then we will see what's going on behind the scenes. So I showed you earlier that today we have externally owned accounts that don't have code that can actually deploy smart contracts with code. That's what we did earlier. So let's do this again, but this time I'm gonna open Anvil, but with this flag, Odyssey. So that means that I'm gonna be able to interact with Anvil using some features of 7702, among many others that Odyssey has. Perfect. So I'm gonna copy this here. So we will be using a deployer, we will be using a delegate contract, which is this. So I have this delegate contract, again, very vulnerable, don't use this please. I'm gonna go over many of similar examples. We actually have in this repository 5 or 7 versions of different broken contracts, so be patient. But I'm gonna be deploying this delegate contract first. So the deployer will actually take this code and deploy it. And then we will have some accounts delegating to this code and we will see what happens with that. So to do this, we actually need to deploy this code. So we deployed it with forced. Now let's store this here. This is actually the address where the code was deployed, right? Because we want to use that later. And we will be calling Alice. And that has a private key and also of course has an address, and Alice will be actually delegating code to this delegate v0 address, right? So if I now I do Alice cast code Alice address, we will see that we don't have code. Okay, perfect. To actually deploy code, we will be using a feature that right now Cast Wallet has. So if we go to Cast Wallet help, we will see this new feature called sign auth that will allow us to sign an EIP 7702 authorization. So to use it, we should do this, and it requires an address, for example. We will be using Alice's private key to deploy code, to delegate to this delegate v0 contract. So Alice will actually be delegating to this contract right here. Okay, so that means that Alice should have somehow be able to execute this code from her account. So to do that, we first need to sign the authorization. If we sign the authorization, we'll see just this raw set of bytes. That's good. But we need to actually kind of send that on chain. That's just an off-chain signature that Alice can do. But we need to actually take that signature and create a type 4 transaction that we saw earlier. So let's first store that data into a variable, and we know we will be using the deployer private key. So in this case, let's say Alice is signing off-chain the authorization to use that delegate contract, and now the deployer will grab that authorization that Alice signed and will send it on-chain. Okay, so now we are creating a transaction from the deployer. Could be anyone, so whoever has this signed authorization can actually do this, and we don't need to specify anything in the to field. We could just set the 0 address in this case. So that's the transaction. See that the transaction type now is 4. Very similar to everything that you have seen so far. So in this case, the sender is the deployer address. It's not Alice. 2 is the 0 address. And we can actually go graph this transaction and see the where's the hash? Oh my god! Oh, sorry, I finished. So, if we actually want to see more details about the transaction, we see that we have a field authorization list. So we have the chain ID, we have the address that we have delegated to. That's the address of where we deployed this contract. The nonce and the signature that Alice produced. Very good. So far so good. So if I do this now, what we should see, sorry, let's clear this up. And if we do Alice address, we shouldn't see an empty code, we should see code in Alice address. Remember that earlier we did this the same with Alice address and Alice didn't have any code, and now Alice has code. But it's kind of a special kind of code, and it's this weird set of bytes, but it's actually quite simple to understand. If we go back to the IP, let's go back to the IP, we see that that code is actually a prefix and an address. That code is actually called a delegation designator, That's a fancy way to say that instead of storing the code in Alice's addresses, what we're actually doing is storing a prefix and a pointer to the address where the code that Alice is using lives in the blockchain. So once this EIP lands on mainnet, whenever you see code on chain starting with this prefix and then you see an address, you will be able to tell that that's probably an external account that has used 7702 to delegate to some other smart account that will live at address. All right. So let's go back to our example. Now we see that we have EF0100, that's the prefix, and then we have the address of the delegate 0 contract. So this 5 FBD blah 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 is the actual address of the delegate B0 contract. Some more things that we can actually try right now, now that we are at it, is that these commands also change. Now we see that the code size of Alice address is of course 23. That's the code size of any address that will be using 7702. And actually the code hash is not, it's interesting to know that it's not the code hash of the actual contract, but it's actually the code hash of what's living in Alice's address. Because if I do code hash delegate B0, the code hash is very different. So when you're reading the code hash of an address that has used 7702 to delegate to another contract, the code hash will be the hash of the contents of that address, which is the code stored at that address, which is this, and not the actual hash of the code that is delegating to. All right. So that does have some implications, such as that the EVM opcodes of external code size, external code hash, external blah blah, those opcodes will behave differently, and actually I have an issue open in Ithaka because I don't think in that testnet that's working okay, and we'll be talking that later. But I want to show you a diagram that should clarify some things about the things that are going on right now. So this is essentially what we are doing in this case, or what should happen in the future. Users will be able to create accounts, probably in some wallets that they will be using, let's say MetaMask or whatever wallet, Ravi or whatever wallet you're using. You will be creating an account. Probably it might be the case that the wallet will give you an address and a private key, yes. But as soon as you do that, you might need to sign a transaction, an off-chain transaction. You won't be spending any gas. And in the transaction that you will sign, you will actually be signing what we just saw, which is a type 4 transaction, that is the set code transaction. You will be signing some data, destination, blah, blah, the value, and an authorization list, right? In the authorization list, you will have the chain ID, you will have the address, that's the address where the code that you're delegating to lives, and your signature. Perfect. Then you take that signed transaction, and because you don't have gas, because you are only kind of a new user of Ethereum, you don't have any gas, you need to send the transaction, to pass that signed transaction to somebody that actually has gas. You can call that a bundler, a relayer, a friend, whomever is willing to send a transaction for you and to pay the gas for you. Probably wallets will have some kind of service that will be able to sponsor your transactions, at least the first ones, so that you create an account with them. All right. Once you send that to, let's call it a relayer, the relayer will actually execute that on chain, will grab the transaction, will execute the transaction on chain. The transaction will reach a node on the blockchain, and the node and the rest of the nodes, of course, what they will do is in your address, they will store the prefix and the address that you have signed here on the type 4 transaction, the green one, where the code lives. So if you actually go to the follow that pointer, we will see that that account has some code, the actual code that you will be executing. So that from now on, any call to this address will be able to execute this code, thanks to this pointer that we have, right? So you call this, the node will read this and will actually be able to execute this. So that means this red code that we have here will be able to govern the behavior of the address, of course, in this chain. Because when you sign the transaction, sorry, I pasted something. So when you sign the transaction, you specify the chain. So this doesn't happen in all chains, which is also a concern. Well, not a concern, but something that we should all take into account for reasons that we'll see later. So there are big questions about who will be able to control that code, whether the code can be upgraded or not, who can upgrade it, who is saying that that code is secure, what if you want to leave that code and you want to migrate to something else, and to some extent, to what extent are you aware of the capabilities of that code? The regular user probably won't be able to tell what the code that MetaMask or whatever other wallet are using in their smart accounts, right? To some extent, should they understand? To some extent, they should be able to tell the powers that they have. And definitely today we don't have the UX to be able to easily inform users about it. It might be a case that also some wallets kind of become gatekeepers, and that's another worry that some people have in the space, because they will be able to tell which accounts you can delegate to. Some of them might decide to do that, and saying that that might be more secure for you because they don't want you to sign any kind of transaction in a phishing attempt to some whatever contract that you end up delegating to, and they end up stealing all your funds. So perhaps wallets might want to whitelist the accounts that you can delegate to, and that might be good, but the other side of the coin is that they kind of become gatekeepers of what you can or cannot do with your account. Then there are risks about migrating. I think about upgradable contracts and all the problems that we have. Well, those problems can be here as well too. So this is a nice diagram. You can copy, you can distribute it, you can use it. I think it kind of summarizes quite well the idea behind 7702 and some of the risks that today we have, particularly about the code. And we have covered 7702 with Cast, but now it's the time to cover 7702 with Forge. In Forge you will find implemented some cheat codes that we will be using throughout this video. It's as easy as going to the VM file, searching for 7702, and we have new functions. One is the assign and attach delegation function, and another one is the sign delegation. These are new cheat codes that we can actually start using in our Foundry tests, Foundry scripts, to be able to leverage 7702 in a relatively easy way. So for example, in sign and attach delegation, we actually use an operator key, we pass an implementation contract, and the next transaction we actually be deploying that. And this is a repository that I'm using and we will be using from now on. In this repository, you will find lots of examples of things that can go wrong in custom 7702 accounts. Of course, not necessarily all of this will go wrong on mainnet. Hopefully none of this will go wrong. And this has nothing to do with the actual implementation of the IPs on the node. So this doesn't mean that the IP is flawed. These are just examples of how developers might run into problems when implementing their custom code. So that's probably why we are already starting to find ways to kind of standardize what an account should or shouldn't do, and have perhaps open source contracts or another libraries. We have their own account implementations, right? Secure and audited and community-based implementations of 7702 accounts. I'm gonna be showing you these different contracts. Again, we have many cases, and for each one of them, I have tests that we will be running, and we'll kind of be exploring the vulnerabilities and running tests to showcase the vulnerabilities and what can go wrong with them. They do increase in complexity, so that means that we will be starting with V0. Some of them are intended to be used in kind of in an upgradable way, and I will be telling you about them so that you understand some issues that can come from, for example, upgrading from V5 to V6. Well, I also left some resources and some future work that we also are planning to implement perhaps in the future, or that you can actually do yourself if you want to fork the repository and implement yourself some vulnerable implementations of a smart account integrating with, for example, the 4337 entry point, or using other signing mechanisms, or using more standardized interfaces. So here we have the delegate contract. Anybody that is delegating to this contract will be really vulnerable, of course, because anybody will be able to execute this execute function and pass whatever code data they want and do whatever they want from this account. So they can actually take value, they can call tokens, they can call other contracts, they can do whatever they want, right? So we have no access controls, and that's like a big vulnerability. I don't think we will see, hopefully we won't see this in mainnet, but just to get started with a very simple implementation, and we'll take it from here. I have some tests for this. All the tests that I'm about to show you do have a similar structure. So we'll be usually using a deployer account, Alice and Bob, that will be delegating to some delegate contract, and the deployer is the one in charge of deploying the delegate contract, okay? First, let's test this idea that anybody can call this function, right? So if we want to actually produce a proof of concept for that, we will be dealing Alice some ether. Let's say Alice has 1 ether in balance at the beginning. We need to build the code we're about to use. Yeah, Bob will be receiving some value from Alice's account, and that's the code that we will be executing with no data. And let's say that Alice, for some reason, signs, let's say she falls for a phishing attempt, and she signs a delegation to this delegate contract. That means that later anybody can call execute on Alice's address, and we'll see that that actually deploys code to Alice's address, and we can actually drain Alice's account. And we don't want that to happen, so probably should be access controls in some way that we're about to see in the next versions. One thing to note is that thanks to this Foundry cheat code, we actually are able to do the sign and attach delegation and do the actual call in the next line. So this actual .execute call that I'm highlighting right here, what it's actually doing is creating a transaction that will be able to both deploy the code, do the delegation, and then do the actual execution. All right. In this case, I'm not using anyone to explicitly to execute this, but you could do like vm.prank Bob, for example, and Bob would be the one relaying this. Okay. Okay. So if we actually execute this, right? Perfect. So this is the test that we have. We see the test dealing some ether to Alice. This is Alice signing the delegation. This is the delegation signature. And then we have someone executing from Alice's account. Look at this Alice execute. This is somebody executing Alice code, passing this data, and actually sending that ether to Bob's account. Another thing that is a little bit more subtle, we don't have a receive function. So if we don't have a receive function, such as in any other smart contract, we won't be able to receive ether. And that's something that we are very used to in externally owned accounts, right? So externally owned accounts can receive ether. But from 7702 onwards, as soon as you delegate to some code, that account will behave as a smart contract. So if we want to actually receive ether, we should actually put a function to receive that ether. Could be a receive function or could be a payall follow-up function. In any case, we also have a test for that. It's very similar to the previous one. So we build the call, we do the sign and attach delegation. I'm about to show you this now. We realize that Alice does have code out, and then if we want to transfer some ether to Alice, you cannot, because there is no receive function. In the trace of the test, you will see exactly the same, but you will see the revert as soon as you want to execute Alice's fallback, because there's no fallback to be executed. So there is a difference here in how I'm sending the delegation transaction. In this case, we are doing the execute call that has attached the data. But know that you don't necessarily need to kind of explicit call to something. You can actually call the zero address with node data just to submit a transaction on chain that has this data attached. Okay, that also works as well in our tests. So you will see me doing this interchangeably, depending on what I want to do or what I want to show. But do know that it's exactly the same, and I won't be using this other method, the sign delegation, because this one I think for me for the tests is easier to use. But you can actually sign the delegation and then attach that delegation to the next transaction and so on. Okay, that's up to you on how you want to do it. Perfect. So let's go to V1 now. I put together a contract that should be a little bit better than the previous one. So let's say we are a developer that we are learning the ropes of 7702, so we have coded something that looks a little bit better. We got fancy, we are using reentrancy guard, we are using errors, we are using events, and we are introducing this notion of guardians that I told you at the beginning of the video, in which, well, perhaps 7702 accounts can actually have guardians, and you can have some guardians do some stuff on your account on your behalf. So the account does have constructor, okay, to set some initial stuff. Then you have the execute function, there is no reentrant, okay, and also implements access control. Okay, I'm about to show you and explain you this line because it's quite interesting and very telling of 7702. And then we have another function to allow guardians to execute something. As long as a guardian is stored in this mapping that is set on the constructor, these guardians will be able to execute from your account. Okay. There are many things for the detailed eye that are going on in this contract, but let's go step by step. And some others I won't tell you, and perhaps you will realize on your own. One thing to note, of course, is that right now this new version can receive Ether, so the developers have improved a little bit. Okay, so now we can receive Ether. That's a big step forward, right? So we might want to deploy this contract, set new guardians, and if we delegate to this contract, we can set our guardians and execute stuff, okay, on our own, or have the guardians execute stuff on us. So before moving on to the tests, let me tell you a little bit about this line. In this line, what we're actually doing is implementing access controls so that calls to this function can only come from this same account, okay? That is not necessarily like a great use case for 7702, because sometimes you might want to have other people execute the stuff on your account, but you might need to have some functions in some cases that require you to be the one doing the execution and not somebody else. This is one way to implement such restriction. The rest of the function is very similar to what we saw in V0. So we have a call, we execute that, and so on and so forth. Perfect. We have the guardians and we can receive Ether. If we go to the tests, in the setup, again, Alice has a code, and Alice will be delegating during the test to this V1 version. It's interesting to know how constructors behave in 7702, and let's use this V1 as an example of that. If I told you that you would be delegating to this account, it might look like you can set guardians during deployment when you are delegating to this account. Okay, I set my guardians, and these guardians will be able to execute stuff, and I will be also myself will be able to execute stuff. And that might be the first impression, but that's very not how 7702 works. When you delegate to an account in 7702, you don't have init code. You don't have initialization code that you can set. There is no notion of a constructor. So that means this constructor executes in the context of when this account is being deployed, not when you are delegating to this account. Those are two very different stages. And actually, the storage of these guardians will be set on the actual delegate contract and not on yours that you are delegating to this contract. Okay, those are very different storages. The one of the delegate account and on the one that is delegating to the account, right? So don't be tricked by this kind of constructors. Always think about where is this constructor actually executing and in which context. Okay, so in this case the guardians would be set at the delegate contract deployment and not on your account that is delegating to it, right? That means that when you are delegating to this, you actually don't have any way to set guardians. Okay, so you won't be able to execute anything on the execute guardian because there is no way to set actually in the beginning those guardians. The guardians can only be set in the constructor of the delegate account, not the one that is delegating to. So be careful with that. In the next version, we'll see how we can actually use initializer functions similar to the ones that you are very used to seeing in proxies to actually set these guardians, okay? But there is one thing to take into account. This constructor might look like it's doing something that is actually not doing that, right? Perfect, so we're actually testing for that here. So for example, the deployer is setting some guardians, just it doesn't make too much sense, but the deployer is setting some guardians, and we're seeing in the test that the guardians are actually set. Then we actually have a test that we show there is no way to set those guardians, okay? So say we have Alice and Bob that want to delegate to the delegate contract. So we have Alice signing the delegation, we have Bob signing the delegation, and anyone that has those delegations can submit a transaction, and that's what we are doing here. So then Alice and Bob will have code deployed, and that code will be the one of the delegate contract we want. All this code, perfect. Remember, when we execute this constructor will not execute. This constructor only executes here, okay? And continuing with the test, we see that neither Alice nor Bob have these guardians set, okay? So that's the test. Let's run it and let's see how that works. Test delegate contract v1. Perfect. Let's see more details because otherwise it's kind of boring. So we have Alice signing the delegation, Bob signing the delegation. We have a call actually doing the delegation itself. Interesting to note that Foundry right now doesn't show you the actual data set in the delegation because you can only see this and you don't have a way to realize this as 7702 transaction that is setting code into this account. So actually I've opened an issue already in Foundry that you should see here. Yes, this one that you will see hopefully in the near future landing on Foundry, a new feature that in the trace we'll actually be able to see more details about the transaction being set or setting code into the account. And then we have the assertions happening. So this example, what I want to show you is the role that constructors play in setting code or not, okay? And the context in which they execute. So be very careful with that when you're developing this kind of contracts or actually reviewing this kind of contracts. I do have the impression that some casual readers might get the sense that, well, yeah, if I delegate to this contract, then I will be able to set guardians, and that's not the case. And that kind of trick can be used probably for more mean purposes. So be very careful with these kind of things. Perhaps you find some other things that are going on here. Let's see. Put that into the comments. Let's say that now we want to move to something more complicated. Let's go to V2. As a new account, again, should be a little bit more complex than the previous one. Look, we don't have a fancy constructor right now. We only have a little constructor that I'm about to tell you what it does. And then we have an initialize function with all the spoilers. And we have an execute function, an execute guardian function. And if you see how these functions are being implemented here, probably you have realized already what's going on here. But anyway, that's not the point. And also we can receive Ether. That's good. The developers still are good with that. Perfect. So this version V2 is about initializing. How do we initialize accounts? Well, we have seen that constructors are not that cool for that, and we need some other way. And we can take lots of inspiration, hopefully the good parts and not the bad parts about upgradable contracts. And we can actually start using initialization functions. In this case, I put a new flag on the storage that is called init and should be able to, ideally should be used to tell whether initialization has happened or not already, and once it's set to true, this cannot be called again, thanks to this require statement. Alright, and there are some spoilers here already. First of all is initialization can be called by anyone. Again, very similar to the lack of access control that we have on v0, now we have that on v2. See that anybody can call this initialize function, and this gets a little bit more complex because you will need to execute a transaction in which you are actually delegating, if you want to do things right, delegating to this account, and at the same time calling the initialize function. If you don't do that, you can be front run and somebody else can initialize your account, your externally owned account, and that's probably problematic for you, and you want that to happen. Okay, so in next versions we will see how this can actually be solved by including signatures and so on and so forth. But in this case, do be mindful that this can be called by anyone, and also in front running scenarios in which somebody wants to initialize your account maliciously. All right. Do note also that we are setting the guardians. Okay, that's good. So the guardians are actually gonna be set on the storage of the account that is delegated into this contract and not on this contract itself. Another thing to take into account is that in the constructor, I'm actually initializing, kind of initializing the implementation such as we do in upgradability. I'm setting the init to true, so that means that this function won't be able to be called on the delegate contract itself. If we didn't have that, somebody could go to the delegate contract itself and call the initialize function. All of that is good, but the developers have really missed the point here because they are not setting init to true. So that means that even if you do everything right and you initialize everything, if you don't set the initialize to true, well, anybody can reinitialize this function. Once again, if you're familiar with upgradable patterns and problems and threats and risks of upgradable patterns, this all should sound very familiar to you. And I do believe that we are gonna have, hopefully not in mainnet, but it might happen, very similar issues to the ones we usually see with upgradability, and we're also going to be seeing something about storage layout in the next version, so bear with me. Okay, so in this case we have seen the lack of access controls, initialization, this idea also of front running initialization of an account delegating to another one in 7.7.02, that's kind of new, and perhaps at some point we should all be mindful of that. And also this idea of not setting the initialization to true, so that means that can be reinitialized. If we go to the test, we will see tests to actually cover that. Very similar to what you just saw. We see that the deployer is deploying the delegate contract v2, then it's checking that the init on the constructor is actually being set correctly, and then anyone can initialize. In this case, we have Alice delegating to the delegate contract. Alice then will have code on her account. Bob or anyone can actually go and set guardians on Alice's account. And once the guardian is set, that guardian can actually do anything, such as taking ether from Alice's account. So in this case, the lack of initialization protection is quite risky because somebody can initialize your account, can set a guardian, and then the guardian can actually execute something and steal your ether, for example. So we should have preventions in place for that. Great, so if we want to go to force and we can actually test that, delegate contract v2, we see the test passing, and we can see more details about it as always. We give Alice some ether, Alice signs the delegation. Again, this could be a phishing attempt, and Alice signs the phishing transaction off-chain and ends up delegating to a malicious contract, and that can be initialized by somebody else, and that somebody else sets guardians on her account, and that somebody else can actually take that ether, right? So here's the initialization being called by Bob, not by Alice, by Bob, and then the guardian call that is actually taking the ether out. So we should have ways to protect these initialization functions, and that's how we move to v3. So now we are on v3, a new version, hopefully a little bit more complex, a little bit more advanced than v2. In v3, we're going to be seeing how we can actually initialize using signatures. Of course, this signature is weak, Splatoon uses, but we're about to see why. execute and execute guardian are exactly the same, so no need to worry about that. The payable receive function is here, so we can receive ether. Perfect. The constructor is also the same as v2, so the initialization cannot happen on the delegate contract itself, but actually should happen via the delegating contract. So far so good. And we also have the require statement to enforce that the contract shouldn't be initialized, and in this case the developers are actually setting the initialization to true so that this cannot be called again. The caller should pass the guardians that want to set and should pass a signature by this address, by this same address. I mean, if this is deployed on Alice's account, Alice should be signing with her private key this initialization data, such that when somebody executes this initialization function passing that signature, this should be authorized and the guardians will be set on this contract's storage. That's the basics of it. If we want to start looking at what's wrong with this, there are a couple of things. First of all is this idea of address this. Be mindful of how address this behaves in the context of a delegate contract or an account delegating to this contract. So it's very similar to a delegate call. It's not the same to call directly this contract, this delegate contract v3. You call it directly, not through a delegating account. Let's call it directly. Call the get hash function, and this address is call will give you the address where the delegate contract v3 is deployed, where it's actually deployed. But if you execute this via delegating account and call initialize, these addresses will actually give you the address of the delegating account, not the address of the delegate contract v3. Alright? So those are very different values. So that might mean that somebody might be tempted to, when they want to build this off-chain signature, they will call the get hash function, they will sign a hash, but that hash will be actually built using the wrong address. So when they sign the hash and send the signature here, this address won't be the same in that execution context, meaning that the signature will be wrong and this cannot be initialized, for example. So do take into account the differences between address this in different contexts. Another thing to take into account is how the signature is built, which is quite weak. Because for example, it's not bound to the chain and it's not bound to the actual delegate contract. So this means that the signature could be reused and neither by time, right? So this signature could be reused in many other contexts, but probably we don't want it to be executed in our context. For example, if we have a similar but a slightly different version of the contract v3, let's call it 3.1, that uses initializable. Instead of using the init flag that we were using here, it's using the good old initializer with the initializable inheritance and so on and so forth, the disable initializers, the good old one that we are all used to. And let's say that on chain we have these two contracts deployed. The way that the initialize function is built in both of them means that on the same chain I can actually reuse that signature across these two contracts. And not only that, but also I could reuse the signature across different chains because we don't have the chain ID here. So we should have the chain ID, we should have an address that is the address where this is deployed. Probably we should get that address here. We're out to see more secure versions in the future. So if we want to go to a test and actually see that, in the setup we're just having Alice sign initialization data, setting a guardian, and then we're deploying in this first test two contracts. So we're deploying the delegate contract v3 and in here the delegate contract v3.1. Alice signs at the beginning the initialization data, but doesn't include the chain ID nor the address of the contract where this is supposed to be executed. It just includes the guardians and her address itself, because for some reason. So you can actually use that signature to initialize the contract v3, but you can actually take that same signature and use it to initialize the contract v3.1. That might be a feature and that might not be a feature depending on the use cases. Probably it's wrong and signatures should be as narrow as possible so that they cannot be arbitrarily reused. So to take that into account. And in the following test, what I'm actually doing is forking a valid testnet of Ithaca, where 7702 is enabled. So I'm showing that you can actually take that same signature that we use on Anvil and initialize the contract on Ithaca itself, on the fork of Ithaca itself. Right? So reinitialization on different chains, signature replace, that kind of things can happen when we are dealing with initialization on 7702 accounts. All right, let's test that just for the sake of completeness. First, we do the simple test. Perfect. And then we do with the traces. So see that in this case, we are doing the initialization, the recovery passes, the delegate contract then is deployed here, and we can actually initialize the second contract with the same signature, and we can do the same on the fork. We fork the testnet on our local environment, we deploy the contract, and we take the same signature and we can use it to initialize on the new contract on a different chain. So that's how signature replace works. Take a look at this, and in the next versions we are about to see how we can actually make this signature a little bit more secure so that we don't run into this like very big problems. All right, see you in V4. So now we are on V4. This is an upgraded version of V3, and actually we are going to be using this as an actual upgradable version of V3, right? So we are going to be testing upgrades of delegating accounts, and we will see how you can actually be delegating to some account and then delegate to another one, and what happens in the process of migrating from one to another, and how things can go actually very wrong. So to make things more interesting, we are actually using the initializable inheritance in this case. We're going to make this contract possible. So we have post state variable here. We have new modifiers to check that signatures are not expired, to check whether functions can be called or not when they are post. And in the constructor, we are doing a new thing. Okay, so we are disabling the initializers, that's okay. And we're also taking the delegate contract address and we're storing that on a mutable variable so that we can actually go and reuse that on initialization function, for example, and others that require a signature, so that we can narrow down the signatures. In this case, the signatures of initialization is a little bit better. We see that people need to actually sign for the guardians, a timestamp until which the signature will be valid, the function they are calling, a hash of the name of the function, the actual address of the contract where this signature is intended to be verified, and also the chain ID. Do note that we could actually be using the 712 structured data. We are not using that because we are lazy. But in production, you should probably be using like more structured data for signing. Then we have the setPost function that actually allows you, for example, to post your external accounts. Now that they are smart, you can actually post them and have some functions be only executable when the things are post or not post, for example. Okay, and to initialize and to post, you should actually be able to supply a signature. In this case, initialization can only be done by you, but the guardians can call the posting function. Good. So during initialization, we recover the signature using a little bit more secure signature than the previous one. I'm not saying that it's flawless, but it's better than the previous one. We do require that the signer is actually the same account where this is being used, and then we set the guardians. And set post is very simple too. It just takes the signature, sets the post, and that's it. And execute, very similar to the one you saw earlier. So what if we wanted to use V4 as an upgrade of V3? Well, the problem is storage. As always, in upgradable contracts, storage is a problem. So do take into account that I made this contract initializable, so init is already gone. We had an init flag here in the previous one, and that is gone. And instead, I put a post state variable that is gonna be determining whether the contract is post or not, right? But that means that if we move to V3 to V4, yes, we're gonna run into storage layout problems, very much the same as in upgradable proxies and that kind of things. So let's go to a test now, because this is easier seen in a test than on a contract. Let's go to before. So I'm going to be deploying the v3 contract and the v4 contract. And Alice will be actually using v3 at the beginning, and then we're going to be moving to v4 and see what happens with that. So here we are on the test of before. We're deploying a v3 contract and a v4 contract. Alice at the beginning has no code, and Alice will be actually first delegating to v3, and then we'll be delegating to v4, and we'll see what happens with that, right? So at the beginning, Alice, to initialize her v3 version, we'll be signing some data. Remember that in v3, initialization function was quite vulnerable, and we only need to sign some basic stuff that didn't work. And that's what we are assigning here. And then Alice will actually sign and attach the delegation and do the initialization. And the storage layout of the delegate contract v3 that you can actually check with force inspect. So if I'm actually taking this, and let's do force inspect. Now we have the storage layout of the v3 version. We have the status that was from the reintrans guard. Then we have the init flag that we had put on v3, and we have the guardians. If you want to see this side by side, you have the init, you have the guardians, and the status come from the reintrans guard, which is this. Okay, so that's the storage layout. And we should be careful when we move to v4, because we could have storage layout problems. If I quickly do this and take the storage layout of v4, I am already noticing that on slot 1, post will be colliding with init, right? Basic storage collision, but we are used to see that on the context of upgradability and proxies and so on and so forth. And in this case, we're actually seeing without proxies, we're seeing on 7702 accounts. And I do believe that's a big problem that we are going to have, because nobody is assuring that when you move, for example, from one wallet to another and you migrate from one delegate account to another, how on earth are we going to be preserving the whole layout and making sure that one doesn't overlaps the other? Hopefully we have some standards for that I think people are working on, but I'm really not sure to what extent that's going to work. So I am a little bit worried about these storage collisions. We'll see what happens. So let's go back to the test. I'm printing here the storage layout of v3, and then moving on to v4. It's as easy as signing a new delegation. We shouldn't be doing anything new. We were delegating to v3 in this case, and then we sign a new delegation, we execute the type v4 transaction, and now we move to the delegate contract v4, and that's it. This is the new storage layout. So what I'm showing in the test is that slot 0 continues to be the status. That's okay, that's set to 0. And now, because we did the initialization of v3 in here, that means that init will be set to 1, that's set to true. And when we move to v4, that same slot will also be set to true. So that means that, and that's what I'm checking here, that the slot 1 is set to 1, meaning true. And that means that in v4, actually, you will be starting in a post state. And due to how v4 is built, it might be the case that it cannot be on post or could be. So we are kind of inheriting some of the old storage that you had in the previous version. Now in v4 you have that as well, meaning that when you are delegating to a new, from your externally owned account to a new account, storage is not cleared. Don't take that into account. Storage is not cleared. So you are delegating to some new code, but the storage is the same. And if the storage is the same, you could run into storage collision problems such as this. So if we actually want to test this, it's very simple. The test won't reveal anything magic, so it's just what we saw right now. We see the test passing, and we can do this. Because the test passes, we see that the initialization is wrong because Alice is already post without having triggered the set post function. So the contract starts in a post state. And that's problematic, and that's how storage collision works in the context of a 7702 account. See you on v5. Now we are on v5. This is one of the last versions that we have built. A little bit more complex than the previous one. Hopefully it has less errors this time. So we are not going to be using this as an upgrade from before. Just imagine that this is a whole new contract. Don't think about it as an upgrade of before. The contract is initializable, has a reentrancy guard, has this post flag that we saw earlier, has the guardians, implements signatures for this initialization that we saw earlier, implements the set post function that we saw earlier, and that all is the same. The execute function is the same, the execute guardian function is the same, and we have included a new function because perhaps you want to use your account to allow people to, from now and then, send funds from your account. Okay, so let's say you have a bag of Ether, and from now on then you want to allow a friend or a third party or a service or whatever to execute something on your account so that they are able to send some value from your account. And you have this one-time send function. You only want them to execute this function once. And this is again related to signatures. If you take a look at the signature, it's very convenient until you realize that there is no nonce management here. So that means that this signature can actually be replayed on this very same function and contract and chain and transform this one-time send function to send as much as you want as long as the valid period is okay. If we go to the actual test, we can see how that signature replay on the same contract works. Having first deployed the v5 contract, we see that Alice has no code. We give Alice some ether, we set the guardian and determine what's the valid until. Then Alice signs the initialization data for this specific contract on this change, on this function valid until a timestamp for only these guardians. Alice does the initialization, now Alice has code, and we want to sign off-chain as Alice. Alice wants to sign the off-chain data to allow somebody else to call this function. So she will actually off-chain sign, put together this data, sign it, produce the actual signature, and give that signature to somebody else, to the one-time sender, for example. And the one-time sender can actually go to this function and execute it multiple times because there is no nonce in here. If we actually execute this, the test passes, and if we see the trace, we see multiple times being executed the one-time send with the same signature. So something that we thought earlier on initialize and set post, that was a relatively more secure signature, we have realized that we are using the same pattern here, but it's insecure, very much insecure for this function specifically. So to make the things better, this kind of signature should actually be, such as in v6, should be using some form of nonce management. So we are actually in v6, you will see that we have a kind of a global nonce in here, and that we are checking with the check nonce function, and each function that uses the nonce is actually incrementing it by 1, again to make the signatures less and less replayable and make them more narrow each time, right? Also in this case we have moved to something a little bit more complex using the pausable inheritance and changing a little bit the set pause function. But essentially in this v5 case and v6 we wanted to show you that something about signatures that we thought was okay for the beginning now is not okay, and we should actually make it more secure. And depending on where you use those patterns can become more or less secure. And that's about it. We don't have a v7, but we do have like ideas for the future, right? To continue extending this repository of vulnerable contracts of 7702 account. We want to introduce integrations with the entry point of port 337 and see how that plays out and what kind of starter vulnerabilities we can introduce there for people to realize what are the safest implementations that they can have so that they don't run into the problems that we are actually including the assign in this repository. We want to also use new signature schemes, such as we have actually Solary has been pretty active in this whole 7702 thing, and they have a library for it, so we might actually use that to introduce some vulnerabilities. And then using some standard interfaces that smart accounts can actually have to kind of standardize the way in which you call them with different modes and so on, so that Wallet and other providers can actually have the same interfaces, and it's easier for front ends to interact with this 7702 account. For more resources, we put a lot of links here on the repository that I encourage you to check out. Of course, the EIP, of course, this other EIP for the interfaces. These examples by the Ithaka team are very cool. And the technical deep dive by the client. Then the Ithaka team has also put together some proof of concept of how to use 7702 on different scenarios, and I think that those are relevant too, and you should check them out. If you want to follow the progress of an actual account for 7702, probably this is a good place to go. In this case, the Ithaka team as well is coding with vectorized an actual account that implements different signature schemes. We can actually take a quick look at that. I think it was this one. Yeah. So you can actually, to interacting with this account, you can actually use different ECSA corps or different kind of signature mechanisms. You will see some cool management of the storage, probably to be mindful of how the storage works in these accounts, and to avoid running into problems that I show you during the video. It does have an iteration with the entry point. It does use 712 signatures. It's far more professional, of course, but it's still a work in progress. So I do encourage you to check this out, to contribute, to see if you want to do something similar, or to suggest to community improvements, or perhaps come up with your own implementations that are better than this, if you can, which could be really cool to have kind of competing implementations that are all secure, hopefully. If you're more of a front-end developer and you want to check out how 7702 can be integrated in scaffold ETH, you have also this repository that you can check out. And if you want to see something already deployed by Optimizer, and that's already on-chain, and you can go to his tweet and see this contract already on-chain that implements some kind of batch execution mechanisms to execute stuff. I show you the issue that we have right now in Foundry open about still not having the traces, but there is an interesting issue as well on the Odyssey testnet, public testnet, that I think we should take a look at and see if I'm right or wrong. But I have this impression that the EVM opcodes are not working correctly on their testnet, because I'm getting different values on where I'm using the Xcode opcodes or calling the contracts from outside the chain. So do be mindful if you're using their testnet and you rely on some of these functionalities, they might not be working okay. But again, the team hasn't confirmed my findings, so it could be a case that I'm wrong. I don't know. Last but not least, let's do a very quick walkthrough of how Geth implements 7702. Alright, so here I'm the Go Ethereum codebase on GitHub, the codebase for Geth, of course. And I just wanted to quickly show you some real code on the node that is handling 7702 transactions. So we have a new type, which is the transaction set code. So the set code is now in Geth. This is the new type that we have on the codebase. And we will see some actual things that we have seen kind of on the EIP and the examples that I show you, but kind of the behind the scenes right now. So we see the delegation prefix, that was this EF0100 that I told you about. We see the structure of a set code transaction that I show you, where it has this authorization list now. So we saw that remember that we saw this on the diagram, this little square that I draw here, that is going on here. So we have the authorization list and we have all the values for the transaction. This is the actual authorization. See that we have the chain ID, the address, the nonce, and the signature. That is exactly what I show you here. And then we have functions to be able to create a signed transaction, to record what's the authority of an account, the transaction data, blah, 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 how to calculate the gas price specified in the EIP. And then if we go to the state transition function, where the transactions are actually done, you can actually see that, for example, we have this pretty known fork between whether the transaction means a contract creation or not, and how the EVM will behave into that. Well, if it's not a contract creation, now we have this new piece of code that says where we should be applying 7702 authorizations. And if we do need to do that, because in the message we have a list of authorizations, we go over each of the authorizations that we have on the list, and we actually go and apply those authorizations on the state transition. Okay, so we can actually go to that function and see how the authorization is actually validated. It recovers the authority, and whether it exists or not already on the state, it will do different things. In here we see incrementing the nonce of the authority. The authority is actually this address in this case, will be the authority. And something that I don't know if I mentioned or not, but if you actually on the transaction, you want to clear the state, you don't want to be delegating to any contract anymore, you actually set that to 0, and that's where it happens on Geth. If it's not 0, you actually will be setting code on a state on the authority. You will be converting that to the delegate, putting the delegation prefix and everything, and setting that into state into the authority. So that's very basic walkthrough of how it works in Geth. But I just wanted to show you the fact that let's see if you can see this. So also I can show you how Geth validates an authorization. First of all, you need to check that the chain ID is okay. You need to check that the nonce is okay. Then you record the authority and making sure that that signature that the authority provided is okay. And then it goes on stuff about the access list and so on. So there's not a lot of things going on. It's not that complex, but exactly that. So I wanted to show you that it's not that complex, that you can actually jump into a Node code base and search for 7702 and start looking on how these things are actually implemented in the nodes. And of course, if you find an issue, report it on the bug bounty program. Otherwise, yeah, take a look at this and just remember that everything is open source in this case, and you can actually not only just read an EIP, which is quite boring, but actually jump into the code and see how it's implemented on the nodes. And actually, as I show you throughout this whole video, on actual more practical examples, more on an upper layer of the stack, seeing how you can build contracts on this, run tests, and really play with this, because this is very close to come into Ethereum. Probably on 2025 this for sure will happen. So we want people to be aware of this, start playing with this, start using tooling about this, start testing testnets, find issues, report them, create standards, contribute to the standards, make talks, workshops, and everything, because I think 7702 is a big feature coming to Ethereum that we should all be worried about in a good sense, you know, like concerned about and paying attention to it and producing material to educate the community of what's coming on the good side and on the more riskier side, that we should be kind of all aware of. All right, so this video was kind of an attempt to raise awareness into 7702, the different risks that it involves, the threats that we have, and particularly show you how you can actually start using Forge and Foundry to play with different kind of implementations, test them, and making sure that they are not as vulnerable as the ones that we have coded here, and as the ones that probably will be showing in the future. All right, so yeah, that's about it. Thank you very much, and see you on the next one.